In this video, we're going to be going over section 2.5 from our textbook, and this is just basic differentiation properties. So these are some rules of differentiation that will allow us to find the derivative of our functions without using the four-step process we saw in the last section, which includes taking the limit of our difference quotient as h goes to 0. So the first thing we'll look at is some notation. So this is the notation for a derivative. If we have a function y is equal to f of x, then f prime of x is the derivative of our function. This can also be written as y prime or dy dx, which is, we would say this as the derivative of y with respect to x, and then d dx of f of x, which is the same thing, the derivative of our function with respect to x. So these are all different ways that we can notate that we're taking the derivative of a function. So the first thing we're going to look at is the constant function rule. So if y is some function of x and it's just a constant function, then our derivative is going to be equal to 0. And we'll look at an example of this. So if we had a function f of x is equal to 3, that is a constant function. And if we were to do the four-step process in this case, we would try to find the derivative by taking the limit of our difference quotient as h goes to 0. And then just looking at our difference quotient, ignoring the limit for a second. We have that this will just be equal to 3 minus 3 because we don't have any values to plug x plus h in for our constant function, and then we're just subtracting our constant function. So we end up with 0 over h, which is equal to 0. So this is why, no matter what, when we have a constant function, the derivative will be equal to 0. And there's a graph here too. We have our f of x, our constant function here, and whenever we have a constant function, it'll just be a horizontal line, and the slope of our horizontal line is always 0. So we would expect that our derivative is equal to 0. All right, so just looking at a few examples of this property. So all of these examples A through D are just constant functions. We have f of x is equal to 3, so what we did up here, and this is why we get 0. We get 0 there for A. We have y is equal to negative 1.4, that's still a constant function. The derivative of that is just going to be 0. And same for this one here, we have y is equal to pi, and pi is just a number. So we have y is equal to a constant function. So our derivative is equal to 0 in this case as well. And then lastly, if we want to find the derivative of our function, constant function 23 with respect to x, that'll just be 0. And if you notice, we saw all of our different notations for the derivative in this example. So f prime of x, y prime, dy dx, and the derivative of our function with respect to x. So just make sure that you're comfortable using these different notations. So the next thing we'll look at is the power rule. So just to recall what a power function is, so if we have a function of the form f of x is equal to x to the k, where k is any real number, this is a power function. And so all of these examples here are examples of power functions. We have x to the power 1, x to the power 2, to the power 3, and the square root of x is going to be x to the power 1/2. Then we have the third root of x, that's going to be x to the power 1/3. And then lastly, we have x to the power negative 3. So these are all examples of power functions. There are many, many different power functions. These are not the only ones, but just make sure that you're comfortable with functions of this form. And so our rule here tells us that if we have a power function, so x to the power n, where n is any real number, then our derivative of that function is going to be equal to this here. It's going to be equal to our power, our n, times our variable to the power of our original exponent minus 1. And additionally, we have our notation here, so y prime and then dy dx. So using this power rule, we are going to find the derivatives of these following examples, these functions, a through d. So first looking at a, in this case, we know that n is equal to 6. We have x to the power 6 here, so just following notation for our power rule, n is 6 here. So then the derivative of our function is going to be n, so in this case 6, times our variable x, and then x is going to be to the power of our original exponent minus 1. So 6 minus 1 is going to be 5. So then our answer is just 6 times x to the power 5. All right, now looking at b here, we have y is x to the power 30. So in this case, n is equal to 30. And if we want to find y prime, we know that we're going to have n multiplying our variable, so 30 times x, and it'll be to the power of our original variable, or original power minus 1, so 29. All right, now doing the same thing for c here, we want to find dy dt for y is equal to t to the negative 2 power. So we would write this as dy dt is equal to, and again, our n here is negative 2, so our negative 2 comes down in front, and then we're multiplying it by our variable, and then our variable is going to be to the power of our original power minus 1, so negative 2 minus 1 is negative 3. And lastly, looking at part D here, we want to find the derivative of our function, which is x to the 3 over 2, with respect to x. And then again, we are going to take our exponent and bring it down in front. Our n is 3 over 2, and then we're multiplying it by our variable, and then our new power is our original power, so 3 over 2 minus 1, so we get 1/2 here. All right, so the next property we're going to look at is the constant multiple property. And this here is the 4-step process of how we essentially get this property. But if we have a function of x, which is equal to some constant times a function of x, and that function of x is going to be differentiable at that value x, we can show using our 4-step process for finding the derivative that the derivative of our constant times a differentiable function is going to be the constant times the derivative of our function. Okay, so you can look through this here, but we're just taking the limit of our difference quotient and showing that if we're given this function here, the derivative of that is going to be this here, where k is some constant and u is some differentiable function at x. And then formally, that is what is written here, our constant multiple property, and then again written in our different notations down here. So what we'll do here is look at some examples of this. So let's look at a here. We're told that f of x is equal to 4 times x to the power 5. And so we have a function here, x to the power 5, multiplied by a constant 4. So our constant multiple property up here tells us that the derivative of this with respect to x is just going to be our constant times the derivative of our function. Now, we have x to the power 5 here, so using the power rule, what we do is bring that 5 down. Then we have x to the power of 5 minus 1, which is 4. So then our derivative for this is going to be 5 times 4, which is 20, x to the power 4. All right, now let's look at problem B. We want to find dy dt for y is equal to t to the power 4 over 12. So first I'm going to rewrite this. It might not be as obvious, but we are multiplying by a constant here, and it is 1 over 12. So actually, I'll write it here. So we have our constant, 1 over 12, and we want to find the derivative of t to the power 4. So again, we have a power function, so we know that our 4 is going to come down in front, and then we're going to have t to the power 4 minus 1, so t cubed. All right, then simplifying this, we're taking a 4 out of this and a 4 out of that, so we end up with 1/3 t cubed, and we can write this as t cubed over 3. All right, looking at example C here, we have y is equal to 1 over 3 times x cubed. So I'm going to rewrite this one as well in the same sense. We have 1 over 3 times 1 over x cubed, and then using our exponent rules, this is the same thing as x to the power -3. So we're bringing this up here into the numerator by changing the sign of our exponent. And I'm doing this just so we can use the power rule, or see how it would be used in this sense. So again, by our constant multiple property up there, we still have this 1/3 out front, and we want to find the derivative of this here. So using our power rule, the -3 will come down in front, and then we have x to the power of -3 minus 1, and that is -4. All right, so then this tells us, this should be y prime is equal to that. This is separate from this y up here. Okay, so y prime is equal to that, and then simplifying, taking out a 3 from here and a 3 from there, we get -1 times x to the -4, which can be rewritten with positive exponents like this here. So that would be our derivative for that one. And lastly, for part D, we want to find the derivative of our function with respect to x. So our function is 0.9 divided by the third root of x. And so I'm going to rewrite this one as well. This is the same as 0.9 times x to the power -1/3. This is because we have the third root of x, so in the denominator we have x to the power +1/3, and then bringing it up, we get -1/3. So now it might be a little easier to figure out the derivative of this function. We have our constant out in front, 0.9, so we'll leave that guy there. And then we want to find the derivative of this one. So we bring our exponent down in front, which is -1/3, and then we multiply by our variable to the power of -1/3 minus 1, so that is -4/3. Now I want to simplify this a little further, and we could do that by using the fact that 0.9 is the same as 9 over 10. And then we still have that we're multiplying by this -1 over 3 here. And have x to the power -4 over 3. Now we can take a 3 out from both of these guys. So then we're left with -3, because we have this negative here, over 10 times x to the -4/3. And then our last step for simplifying this, I'll rewrite this as a decimal, which will just be 0.3, and then we'll bring this down to the bottom so we can write this with positive exponents. So we get -0.3 over x to the 4/3 power. And that would be our derivative there. Okay, so that's how we can use the constant multiple property. The next thing we'll look at is our sum and difference property. So in this case, we can prove it essentially doing the same thing that we did here for the constant multiple property using the 4-step process. And when doing so, we find that if we have a function f of x, which is the sum of two functions, then the derivative of the sum of these two functions is going to be the sum of the derivatives of these functions. I know that was a little bit of a mouthful, um, but doing the same process, we can also see that the derivative of the difference of two differentiable functions is going to be the difference of the derivatives of the functions. And so that's all that means here, this plus or minus. We're saying this is the case if we were to add two functions or subtract them. And then again, we have our different notations here. So what we'll do is, of course, look at some examples so we can make sure we understand this. So let's do part A first. So we have this function here, f of x is here, and we know from our sum and difference property that if we want to find the derivative of functions that are being added or subtracted together, so like this here, we can find the derivatives of each of them individually. So what we'll do first is, I'll do some color coding. So we're going to look at 3 times x to the power 4 first. So we're going to use a couple different rules here. Remember our constant multiple rule? So we have a 3 multiplying our function. And then we also are going to use our power rule here. So our 4 comes down in front, and then we have x to the power 4 minus 1, which is 3. Then we can do the same thing for our 2x cubed here. And don't forget we're subtracting that out, so we keep that minus sign there. Constant multiple tells us that 2 stays there. Power rule tells us the 3 comes down in front. And then we have x to the power 3 minus 1, which is 2. All right, let's do this one now. So we're adding x squared. So we want to figure out the derivative of x squared. So the 2 comes down in front by our power rule. And then our exponent is now going to be 2 minus 1. So that'll be 2 times x to the power 2 minus 1, which is just to the power 1. And then we usually don't write 1, so we can just keep it like that. Now looking at our next term, we have minus 5x. So we're going to keep that minus sign there. Our multiple out in front is 5, so that stays there. And we're going to multiply by the derivative of x using our power rule. We know that we have x to the power 1, so 1's going to come down in front. So I'll just write that there. And then we have x to the power 1 minus 1. So that looks like x to the power 0. And then lastly, we know that we have a constant here, the 7, and we know from the beginning of this video that the derivative of a constant function is just going to be 0. So we just add a 0 there, but we don't have to write that. Okay, so simplifying everything, we have 3 times 4 is 12x cubed. Then we have minus 2 times 3, so 6, and then x squared, plus 2x. And then minus, we have 5 times 1 times x to the power 0. Well, we know 5 times 1 is just going to be 5. And x to the power 0 is just going to be 1. Anything to the power 0 is 1. So this is our final answer for our derivative. All right, let's do the same for example B. This is our function here, y is equal to 3 minus 7x to the negative 2 power. So we will write this as y prime, staying consistent with the notation. So first we'll look at the derivative of 3. That's a constant, so we know it's just going to be 0. So we'll just write this here to stay consistent. Then we are going to 0. All right, then we are going to find the derivative of this 7x to the power negative 2. So we have this minus sign here. 7 is a constant, so we'll keep that out in front. And then our power rule tells us that this negative 2 is going to come down in front here. So negative 2 times x to the power negative 2 minus 1. So negative 3. Now simplifying this, we get negative, actually we don't, we have negative 7 times 2, negative 2. So this is positive 14. and then x to the negative 3, and then rewriting this as positive exponents, we have 14 over x cubed. All right, let's look at part C here. We're given y is equal to 5v cubed minus the fourth root of v. And so we'll write our derivative as this. So again, we're going to look at everything separately. So let's find the derivative of 5v cubed first. Constant multiple property and power property tells us we're going to take 5 times 3, v to the power 2. And then we'll subtract out the derivative of this guy here. And actually, real quick, before we do that, I'm just going to rewrite the fourth root of v as v to the power 1/4, just so we can easily see what's going on with the power rule. So what would happen in this case is this 1/4 would come down to the front. So we have 1/4 v to the power 1/4 minus 1, which is negative 3/4. All right, then multiplying this out, we get 15 v squared minus, we're going to have, writing this as positive exponents, we have 1/4 v to the 3/4 power. All right, and that is our derivative for that guy. Lastly, looking at part D, this is our function here. So f of x is equal to this here. And what I'm going to do is, again, rewrite these guys so we can easily see what's going on with the power rule. So rewriting our function, we have negative 3/4 is our constant, and we're multiplying that by x to the power negative 1. So we have this x in the denominator there. Then we're adding 4 is our constant times x to the power negative 3, because again, we have this 3 in the denominator there. And then we're subtracting out 1/8 is our constant, and we're multiplying that by x to the power 4. All right. So now let's look at what the derivative would be, and just to keep consistent with notation, that's how we write the derivative in this case. So let's look at each term individually again. We have our negative 3/4, and then x to the power negative 1. So taking the derivative of that using the power rule, the negative 1 comes down, and then we have x to the power negative 1 minus 1, which is negative 2. Then this second term here, we have 4 times x to the power negative 3. So this 4 stays here. This negative 3 will come down in front. And then we have x to the power negative 3 minus 1, which is x to the power negative 4. Lastly, we'll look at this term here. So we have this minus sign still out front. We have our multiple still out front. Then our power is going to come down in front, and we have x to the power 4 minus 1, so then x cubed. All right, now simplifying everything out, we see that these negatives cancel here, so we're just left with 3/4 times x to the power negative 2. Then we have 4 times negative 3, so we're going to get negative 12, and then x to the power negative 4. Lastly, we have this 1/8 times 4, so we can take out a 4 from both of these guys. This minus sign will stay here, and then we're left with 1/2 times x cubed. And the very last step is going to be rewriting these exponents so that they're positive. So we get 3/4 x squared minus 12 over x 4 minus, we can write this as x cubed over 2. Right, so this would be our derivative of this function here with respect to x. All right. Something else that we want to go over is rewriting our functions before differentiating. So it'll be helpful to rewrite functions so that we can work with essentially simpler functions and use those rules of differentiation that we just went over. And that's kind of what I was doing in this example here, especially with part C and D. I rewrote the fourth root here as this, just so it was easier to see what's going on. And then same with these terms here. I just rewrote everything so that it was clear what rules we were using. So yeah, we're going to do that for this example here. So rewriting this rational function here, we have that this is equal to 5 over x minus 3x over x plus 4x squared over x. So this is equal to this. We're just splitting up the fractions. Then rewriting and simplifying, we have 5 over x, so bringing that x into the numerator, we have 5x to the negative 1. These x's here cancel, so we're just left with minus 3. And then these x's will also cancel, so we're left with plus 4x. All right, so now this is much easier to work with than this rational function here, and we can find the derivative of this guy. So first term, we have 5 times x to the power negative 1. So our constant will stay out in front. Our exponent will come down, and then we have x to the power negative 1 minus 1, so negative 2. Then we're going to look at the derivative of this guy. It's just a constant, so its derivative is 0. So I'll just write this 0 for us. And then taking the derivative of this guy, this 4 stays out in front. And then we have 1, because we have x to the power 1 here, times x to the power 1 minus 1, so x to the power 0. Simplifying, we get negative 5 times x to the power negative 2, and then we know that x to the power 0 is just going to be 1, so we just have 4 times 1 times 1, so that's just 4. And then simplifying one step further by getting all positive exponents, we have negative 5 over x squared plus 4. And so this would be our derivative of this function, and that's why it would be much easier to rewrite functions so that we can use the rules that we just went over. All right, so the next example we're going to look at is instantaneous velocity. So an object moves along the y-axis in feet so that its position at a certain time in seconds is given by this function here. So first we want to find the instantaneous velocity of our function. And remember from our last video, this is the same as the derivative of our function. So for part A, what we want to do is find the derivative of this guy. So f prime of x, our derivative, what we'll do is, again, we'll take the derivative of each of these terms individually. So using the power rule in the first term, the 3 comes down, then we have x squared. Then we have that this 15 stays here, the 2 will come down, then we have x to the power 1. And then our last term here, we have 72x. So again, the 72 stays there, and then we have x to the power 1 minus 1, so that will just be 1. And then fully simplifying, we get 3x squared minus 30x plus 72. All right, so that is our instantaneous velocity. Then for part B, we want to find the velocity at 2 seconds and again at 5 seconds. So all this means is that we're going to plug in these x values into our derivative. So first, actually, right, so at x equals 2 seconds, we plug 2 into our derivative. So we get 3 times 2 squared minus 3 times 2 plus 72. This will be 12, 60 plus 72, and that'll be 24. Right, and this will be 24 feet per second. Can't forget our units. And then at x is equal to, was it 5? Well, again, just plug 5 into our derivative for x. So we get 3, 5 squared minus 30 times 5 plus 72. This is going to be 3 times 25 minus 150 plus 72. So then we just get 75 minus 150, so that's 75 plus 72, so we get negative 3. All right, and then lastly, we want to find the times when our velocity is equal to 0. So we know from part A that our velocity is given by this, our derivative here, so we're going to find when our velocity is equal to 0, aka when this function is equal to 0. So when our derivative is equal to 0, we'll set our function equal to 0, and then we can just factor. First thing we'll do is take a 3 out from each term, so then we're left with x squared minus 10x plus 24. And then this turns into a pretty simple factoring. We need two numbers that'll multiply to be 24 and add to be 10. And we need positive 24 and negative 10. So that'll be negative 6, negative 4. All right, so at x is equal to 4 and x is equal to 6 seconds, our velocity will be equal to 0. All right, now the last thing we're going to look at is tangents. So we are given this function here, and first thing we want to do is find the derivative. So we'll use our power rule on the first term, so we get 4x cubed. Then we have power rule on the next one, as well as our constant multiple rule. So that is 8 times 3, so 24, and then x to the power 2. And then we just have a constant 7 here, so the derivative of that will just be 0. All right, so that's it for part A. For part B, we want to find the equation of the tangent line at x is equal to 1. So what we'll do for this one is use point-slope form. This is because at x is equal to 1, we will have 1 point, and then since we found this derivative here, we will have the slope at that point. So what I mean is we're going to use this form here. This is point-slope form. So the first thing we got to do is find our y1 here. So y1 is going to be, if we were to plug our x1 into our function, and our x1 is given by this here. So we plug 1 into our function, we'll get 1 to the power 4. We'll get this here, so we get 1 minus 8 plus 7. So we just get 0 there. And the next thing we want to do is find our slope. And we know that the slope is our derivative, and then we want to find the slope at this point. So we'll plug in 1 into our derivative. So we get 4 times 1 cubed minus 24 times 1 squared. And that'll just be negative 20. All right, now plugging this into our point-slope form, we have y minus y1, which we found to be 0. Then we have m, which we found to be negative 20. Then we have x minus x1, which we are given as 1. Times x minus 1. So this is our answer here. That'll be our equation of the tangent line at that point, x is equal to 1. And then lastly, we want to find the values of x where the tangent line will be horizontal. So we know that the tangent line will be horizontal when our derivative f prime of x is going to be equal to 0. Horizontal line implies our slope is 0. And we saw that in the beginning of this video. All right, so plugging or figuring out when our derivative will be equal to 0, we'll just set it equal to 0 and factor. So pulling out a 4x squared in both terms, we're left with x minus 6 here. And then this just comes out to x equals 0 and x is equal to 6. So for these x values, our slope is equal to 0 and therefore our tangent line is horizontal. All right, so that is it for this video.